In this video, we will discuss properties of logarithms. Recall the two important bases we have discussed for logarithms. We have base 10, which are common logarithms, and base e, which is called natural logarithms. We can see here that our base is shown with the logarithm, base 10, and we have log of base 10, which is commonly written as log without any base shown. So if there's no base shown with a logarithm, then we assume that it is base 10, and that's the log button on your calculator. And base e, where e is Euler's number, and we can denote it as log of base e, or it's commonly shown as ln, ln, which is ln on your calculator, sometimes both capital letters or lowercase. Evaluate the following examples on your calculator. We have log of 10. This is assumed to be log of base 10, and we know that we have log of base 10 of 10, and that is equal to 1. Next, we have ln of e. For this, you'll need to use two buttons on your calculator. First, you put in ln, and you may have an e or just an e to the power of x. Note that if you have an e to the x button, you'll need to put in an exponent of 1. So that's equivalent. That step isn't required to be shown, but that is also equal to 1. So log of 10 and ln of e are both equal to 1. We also have log of 1,000, which is equal to 3, and ln of e to the minus 2, this is equal to negative 2. So before we want to proceed any further, I just want to show that we can rewrite this 1,000 as 10 to the power of 3. So log of base 10 of 10 to the power of 3 is equal to 3. So these results may be surprising to you that they end up being whole numbers, but we'll look at the properties that support these ideas in a moment. Before we discuss the laws of logarithms, I want to remind you that we have a relationship between the logarithmic equation, y is equal to log of base b of x, and its equivalent exponential equation, which is x is equal to b to the power of y. And using what we know about exponent rules, we can relate those rules to logarithms. The first law is the product rule. So we have log of m times n is equal to log of m plus log of n. Next, we have the log quotient rule, where log of m divided by n is equal to log of m minus log of n. With the log power rule, we have that log of m to the power of n is equal to n multiplied by log of m. Next, we have the logarithm of 1. Log of 1 is equal to 0, and this relates to anything to the power of 0 is equal to 1. If we take log of base b of b, that is also equal to 1. And log of base b of b to the power of n is equal to n. Rule number 6 relates to number 5 because we can use our power rule. So first you use rule 3, where log of base b of b to the n is equal to n multiplied by log of base b of b, using the power rule. And now using the log of base rule, we know that log of base b of b is equal to 1. Therefore, this entire expression reduces to n. Rule 7 states that b to the power of log of base b of x is equal to x. And last but not least, Rule 8 states that log of base a of n is equal to log of base b of n divided by log of base b of a. This is called your change of base formula. And the reason why this is helpful is that our calculators only have logarithms of base 10 and base e on them. And if we want to evaluate a logarithm of a different base, such as base a, shown here, we can use either the log of base 10 or log of base e, ln, to calculate the original question. And I'm going to actually just go back a couple pages and look at a couple examples of how we could have used that to evaluate the given expressions. Now, looking back on page 7 of your notes, you can see where we introduced logarithmic functions. I said that we would come back and evaluate this example later, because at the time we didn't know the change of base formula, so we couldn't evaluate this in our calculator. And what we can do is evaluate this as log of base 10, so log of 24 divided by log of our base, which is 2.48. And we end up finding that it is equal to approximately 3.49906. Okay, so that is how we can evaluate a logarithm of a base other than base 10 or e. It's worth noting that we could have done the change of base formula using ln. So we could have done ln of 24 divided by ln of 2.48, and we would also arrive at the same answer. If we also take a look at page 6 of our notes, we had evaluated log of 40 divided by log of 5 and ln of 40 divided by ln of 5, and we found that they had the same result. So these would have been results of our change of base formula, which would be log of base 5 of 40, and the change of base formula was just applied using the base 10 here and base e. But you see that you do arrive at the same answer of 2.29. Back to page 7 of our notes. Now that we've reviewed all the logarithm properties, we're going to go over some examples of how to simplify logarithmic expressions and also expand them out. So in these examples, we're going to simplify as much as possible after the initial step that is suggested. And give a final answer. So the first one, it says write as a single log. We have log of base 3 of 5 plus log of base 3 of w, and we want to combine it as a single log. We can only combine these two logs because they both have the same base. So our final expression will have a log of base 3, and using the product rule, we get 5w. So we take 5 and w and multiply them together to combine it as a single log of the same base, so base 3. Example 2, we now have a single log, so log of base 5 of 25 times a times b, and we want to write this as a sum of logs. Okay, so we have the product of 25a as well as b, and we can expand this out using logs of the same base, so log of base 5 of 25 plus log of base 5 of a plus log of base 5 of b. Now the only term that can be simplified is the first one. So we have log of base 5 of 25, which can be rewritten as 5 squared, plus log of base 5 of a plus log of base 5 of b. Now we can simplify further by evaluating log of base 5 of 5 squared. We know that is equal to 2. Since our base and the base of the exponent within the logarithm is the same, so this can be written as 2 plus log of base 5 of a plus log of base 5 of b. Question 3 says write as a single log. Notice both of my logs have the same base of 3, and we combine these into the same logarithm, so we'll also have a logarithm of the same base by applying the quotient rule. Because we're subtracting two logs, we can rewrite them as a single log with division, so log of base 3 of 5 divided by w. Question 4 says write as a difference of logs. So we know it's going to be a difference of logs because we have log of a quotient. You can rewrite this using subtraction. So log of base 5 of t minus log of base 5 of 125. Recall 125 can be written as 5 to the power of 3, and log of base 5 of 5 to the power of 3 simplifies to 3. So we can write this as log of base 5 of t minus 3. In question 5, we're asked to write as a product. So we have log of base 2 of 16 to the power of x. We can take that exponent out front and express it as x times log of base 2 of 16, which can be simplified further. So we have 16 can luckily be expressed as a power of base 4. So we can write 16 as 2 to the power of 4. Now this simplifies further as x times 4 times log of base 2 of 2. But we know that log of base 2 of 2 is just 1. So this reduces to 4 times x. Question 6 says write as a single log. Given 4 times log x plus half times log of y minus 5 times log of z. All of these logarithms have the same base 10. So we can combine them as a single log. Remember that if you have a coefficient, so we have a few coefficients, one in front of every term. In fact, we have a 4, 1/2, and a -5. Those can be written as exponents within the logs. So the first term can be written as log of x to the power of 4. Then we have plus log of y to the power of 1/2 minus log of z to the power of 5. Remember that y to the 1/2 is just equal to the square root of y. So now using the product and the quotient rules for logarithms, we can simplify this as log of x to the 4 times the square root of y divided by z to the power of 5. And in question 7, we want to expand out this logarithm to be a sum or difference of logs, as well as constants multiplied by logs where applicable. So we have log of base 3 of 27 times x times y squared divided by the 5th root of z. First, we can take everything that is a product and write it as a sum of logs. So log of base 3 of 27 plus log of base 3 of x plus log of base 3 of y squared. And because the 5th root of z is in the denominator, we can rewrite that as subtraction. So z of base 3 of the 5th root of z. Now taking each of the exponents within the logarithm, so we can pull that exponent out front of the log. And that only applies to the last two terms. So these last two terms we can express as 2 times log of base 3 of y minus 1/5 times log of base 3 of z. Our first term can be further simplified because log of base 3 of 27 can be simplified to, well, 27 is 3 to the power of 3, so we can simplify this as 3 plus log of base 3 of x. In this next example, we have a few examples where we can practice using the change of base formula. I mean, you could apply other rules to solve them as well, but we can evaluate this by taking the log of 625 divided by log of the base to solve for the value. So attempt each of these questions by applying the change of base formula and compare your solutions to what is posted here. There's also some practice Kahoot problems, and we'll be looking at those in seminar. We now have the basics to solve exponential equations. And a lot of the time with exponential equations, we just need to practice to implement each of the properties that we know about logarithms and exponents. So, see you in the next video.